Welcome to the deep dive. Today we are strapping in to tackle the massive complex brain of AI, large language models. If you've ever asked ChatGPT to draft an email or, use Gemini to summarize a dense report, you've experienced what these things can do.
You've been on the receiving end, yeah.
Exactly.
Yeah.
And we have a huge stack of source material here. It's essentially the condensed technical knowledge used by top AI researchers. It's a gold mine of high-leverage insights.
It really is.
Our mission isn't to quiz you, but to give you a definitive shortcut to understanding the engineering schematic of modern AI. What these systems are, the revolutionary architecture that powers them, and, well, the clever efficiency hacks that make them affordable to run.
Absolutely. And the foundational problem being solved here is a translation challenge of, epic proportions. It's about bridging this vast, messy gap between human language.
A world of context and nuance.
Exactly. Our evolving semantics and the rigid, purely numerical world of computers. Language is fluid, but machines demand structure. Precision. So we're going to pull back the curtain on the fundamental mechanisms that allow these models to appear so intelligent, focusing on the key innovations with analogies that actually stick.
So think of this deep dive as the definitive guide to moving past just using AI and actually understanding its true limitations and, of course, its potential. That's right. And this is crucial knowledge because it underpins every major AI tool you use. We're aiming for those serious aha moments.
Yeah.
And to get there, we have to start at the absolute foundation. At the most minute level, how human text is first converted into something a computer can even process.
All right, let's start with the definition. A foundational concept in our source material asks, what truly defines a large language model?
Right, the LLM.
Fundamentally, LLMs are complex AI systems trained on vast text corpora. We're talking trillions of words, often designed to understand and generate human-like language.
And the large part is key.
The large part is the defining feature. It refers to the sheer scale. They possess billions, sometimes trillions of parameters. And these parameters are just the internal variables the model adjusts during training to learn.
Billions of parameters. That's the raw capacity. That's the complexity we're dealing with. And we know these models are now masters of core tasks. Things like high-quality translation, in-depth summarization, nuanced question answering. But if they're just predicting the next word, how are they so different from the simple statistical models like n-grams that we used 15 or 20 years ago for, basic autofill?
That's the key distinction, and it really highlights the architectural leap. Traditional models like n-grams, they relied on simplicity. They tracked sequential probability.
So just what word comes next?
Literally. They just calculated how likely one word was to follow one or two words immediately before it. Their memory was, it was non-existent. They couldn't handle context beyond a very short sequence.
Oh, I see.
LLMs, by contrast, use massive data sets and, crucially, the revolutionary transformer architecture. And this allows them to process long-range dependencies, connecting words across entire paragraphs and contextual embeddings, making their understanding dramatically more sophisticated.
So they don't just know what word is likely to come next.
They know what the entire conversation means.
Okay, so the foundation of the intelligence isn't just the sheer amount of data, but the architectural tool, the transformer, that can actually make sense of that data across huge distances.
Exactly.
Okay, let's unpack this journey from messy human text to precise machine processing, starting with step one, tokenization. You called it the critical language bridge.
Tokenization is the necessary translation layer. The core problem is that LLMs process numbers and vectors, not, raw text strings.
Right, computers need numbers.
The solution is tokenization, which systematically breaks down raw text into discrete, manageable units called tokens. And these tokens can sometimes be full words, sometimes subwords, or occasionally just characters.
Let's use a tangible example. If I type a word like artificial, it might be split into 3 tokens: art, ethic, and IO. Why do that? Why not just treat artificial as a single token?
It's primarily about 2 things: efficiency and robustness. If you try to use every unique word as a token, your vocabulary size just explodes.
It would be enormous.
But if you use subwords, you can keep the vocabulary manageable, say 50,000 common units, and still reconstruct virtually any word in the language.
And that robustness comes into play when the model sees an out-of-vocabulary, or OOV, word, right? The word it's never seen before.
Exactly. OOV words are the Achilles heel of simple tokenizers. If the model encounters a brand new, highly specific word, maybe a new piece of financial jargon like cryptocurrency back in 2012.
Or a rare name.
or a very rare proper noun and it hasn't seen that exact sequence before, it could treat the entire word as an unknown, and you lose all potential meaning.
So what's the fix, technically speaking?
The standard fix is subword tokenization, specifically using a technique called byte-pair encoding, or BPE. BPE works by iteratively merging the most frequent adjacent pairs of characters or subwords in the training data until a target vocabulary size is met. So, when the model sees cryptocurrency, it splits it into known, semantically relevant units like crypto and currency.
Wait, I need to make sure I understand the magnitude of this innovation. By splitting cryptocurrency, the model doesn't see a complete unknown. Instead, it understands the meaning of crypto and the meaning of currency, which are already in its vocabulary.
Precisely.
So BPE ensures robust language processing because even if a word is new, its components probably aren't. And that maximizes efficiency and minimizes data waste.
Exactly. It's a genius compression strategy that maximizes the efficiency of the model's vocabulary while minimizing the chance of encountering a total unknown. Without robust tokenization, the entire thing just collapses.
Perfect. So we have token-structured manageable chunks of text. But how does the LLM give these tokens meaning? How do we translate that token, whether it's art or the, into a concept that lives in the machine's numerical world? That brings us to step 2, embeddings.
Embeddings are where semantics meet advanced mathematics. They are dense vectors, effectively long lists of numbers, that represent each token in a high-dimensional continuous space.
Okay.
Think of the LLM's mind as this massive multidimensional map where every concept, every word, lives as a specific coordinate point.
I like that, a map.
And the critical insight is that related concepts live close to each other. The embedding for king might be close to queen and man, but really far from pineapple or sky. These vectors capture the token's semantic and syntactic properties.
Proximity equals relevance. That's a powerful visual. But if these vectors are just lists of numbers, how does the model initially decide the coordinates for king?
Well, they are often initialized randomly or sometimes started with pre-trained statistical word models like GLOVE, which already have some idea of word relationships.
But that's just a starting point.
Right. The real magic happens during the massive training phase. These vectors are constantly refined via gradients computed during backpropagation, which is the primary method by which neural networks learn.
Okay, let's unpack that process of refinement. So the LLM processes text, generates a predicted output, and then compares that to the correct answer, calculating the loss, or the error. The goal is always to minimize that loss.
Exactly. And to minimize loss, the model needs to know precisely how much to adjust every single parameter, including the thousands of coordinates in those embedding vectors.
And that's where the math comes in.
This is where the chain rule, a fundamental concept in calculus, is applied across the model's deep, layered architecture. We use the chain rule to compute gradients layer by layer, essentially telling the model, you need to adjust coordinate 42 of the king vector by 0.0003 units in this direction to reduce your error.
So if the model incorrectly links, say, dog with automobile during a prediction, the gradient calculation during backpropagation tells the embedding of dog to move away from the numerical space of automobile and closer to the space of cat or pet.
That's the perfect intuition. And because the models are so vast and the data flows through so many layers, the math involved in managing these updates requires specialized tools to maintain precision and stability.
And this is where we see these heavy-duty calculus concepts, like the Jacobian matrix. Why is a tool like that necessary here?
The Jacobian matrix is essential because the LLM isn't dealing with simple scalar outputs. It's dealing with complex, multidimensional vector outputs at every single layer.
Right.
The Jacobian captures the partial derivatives of all outputs with respect to all inputs simultaneously. It's like a comprehensive instruction manual for adjusting every single coordinate in a vector.
So it manages ripple effects across all those numerical dimensions.
Exactly. It ensures that when the embedding for king is adjusted, all of its components, its masculinity, its royalty, its closeness to queen, are updated accurately and cohesively. It maintains precision.
And we also need mechanisms to ensure the training doesn't just fall apart or get stuck, which brings us to tools like the ReLU functions derivative and KL divergence.
Right. The ReLU activation function, which determines if a neuron fires, has a very simple derivative. It's either 1 or 0. This simplicity helps prevent the problem of vanishing gradients.
Where the model just stops learning.
Exactly, where the gradients get so tiny that learning grinds to a halt. The simplicity of ReLU keeps the learning momentum going.
And KL divergence. That's about checking the quality of the model's predictions, correct?
It is. KL divergence, or Kullback-Leibler divergence, measures how well the model's predicted probability distribution matches the true or target probability distribution. It's used as a metric or sometimes as part of the loss function to guide fine-tuning.
So it makes sure the model isn't just getting the right answer by accident.
Right. It makes sure the confidence in its prediction aligns with the reality of the data.
So all these sophisticated mathematical tools, Jacobian, ReLU, KL divergence, are ultimately focused on one thing: making those embedding vectors as semantically accurate and stable as possible.
That's the goal.
They ensure that when the LLM sees the number 42, it knows that 42 represents the precise meaning of the word dog in that specific contextual scenario.
Precisely. We've tokenized the text, and we've given those tokens meaningful, refined numerical vectors. Now we need the engine that takes those vectors and weaves them into coherent meaning.
The transformer. This is the architectural triumph that allowed LLMs to scale into the behemoths we know today. To understand how revolutionary it was, we have to look back at what came before. Sequence-to-sequence models, which often relied on recurrent neural networks, or RNNs. What were the specific debilitating limitations that the transformers successfully overcame?
The limitations of RNNs were, well, they were numerous, but they centered on two main issues: speed and memory.
Good.
RNNs process tokens strictly sequentially. Imagine trying to understand a 500-page book word by word, and you can only calculate the meaning of the current word based on the one immediately preceding it.
That sounds incredibly slow.
This sequential bottleneck made training excruciatingly slow. We're talking months, even for smaller data sets.
And the memory problem, the long-range dependency failure.
That was the biggest semantic failure. If the model had to track a dependency over a long sentence, say 50 tokens, the RNN struggled immensely. Information from the beginning of the sequence would just vanish by the time it reached the end.
Can you give an example?
Sure. If you said, the CEO who flew to Tokyo last week to meet with investors finally announced the acquisition, an RNN might forget that the subject CEO was singular by the time it got to the verb announced.
So the transformer's fundamental shift was moving away from that sequential processing, that slow train on one track, to massive, efficient parallel processing, many tracks running simultaneously.
Exactly. The transformer architecture solved this by completely eliminating recurrence and enabling parallel processing via the self-attention mechanism. Every token can be processed simultaneously, which drastically cuts training time.
And critically.
And critically, every token can immediately look at every other token, solving the long-range dependency problem instantly. This leap in scalability and contextual understanding is why transformers dominate.
And here's where it gets really interesting: the attention mechanism. This is often cited as the single biggest intellectual leap in modern AI. Let's dive deep into its core concept. What exactly is attention doing?
The core concept is dynamic focus. Attention allows the LLM to dynamically weigh the importance of different tokens in a sequence when either interpreting the input or generating the output.
So instead of treating every word equally.
Right. Instead of treating every word in a 100-token input equally, the attention mechanism calculates for every single word how relevant every other word is to its meaning.
So the immediate practical impact is a radical improvement in context understanding, especially over long distances. If I write, the architect presented her design to the committee, but they rejected it because the costs were too high, attention helps the model definitively link it back to design and they back to committee, even with all that other stuff in between.
That's the essence of it. It's what gives the LLM that human-like ability to track subjects and objects cohesively.
But how does it actually quantify that relevance? This is where the famous query, key, and value vectors Q, K, V come into play.
It's a precise mathematical negotiation. Every input embedding is transformed into three distinct vector representations: the query Q, the key K, and the value V.
Okay.
So when the model focuses on a specific token, the query, it calculates similarity scores against all the keys, all the other tokens in the context. This similarity calculation is usually performed efficiently using the dot product.
So the dot product computes the degree of similarity. A high score means the key token is highly relevant to the query token.
Correct. We get a set of raw, unnormalized similarity scores. However, this process has a monumental catch that impacts real-world deployment: the computational requirement.
Oh.
Calculating attention involves comparing every token to every other token, meaning the computation is quadratic complexity, or dollar where $1 is the sequence length.
Wait, if I double the length of my input prompt, I don't just double the computational cost.
You quadruple it. Exactly. That quadratic complexity is precisely why context windows are so computationally expensive and why a model with a 100,000 token window costs exponentially more than one with a 4,000 token window.
That puts the high cost of running these things into very concrete terms.
It's what drives all the research into efficiency techniques like sparse attention, but for standard transformers, it's the harsh reality.
Okay, we have these raw, expensive similarity scores. They're just raw numbers, positive and negative. How do we turn them into usable, weighted percentages of focus?
That's the crucial job of the softmax function. Softmax takes those raw, scaled similarity scores and normalizes them into a probability distribution. It converts the scores into positive weights that all sum up to exactly 1.
I see.
This forces the model to emphasize the relevant tokens and effectively ignore the irrelevant ones, ensuring the computational focus is pinned to the contextually important parts of the input.
So the attention mechanism tells the model where to look, and softmax turns that focus into a precise, quantifiable amount of energy. Like a percentage of its power, it dedicates to that specific word.
Perfect analogy. And we amplify the intelligence of the system dramatically by introducing multi-head attention.
Right.
Instead of running attention just once, we split the query key and value vectors into multiple smaller subspaces and run several parallel attention calculations simultaneously.
Why complicate it with multiple heads? Why not just one massive attention mechanism?
It's about capturing different kinds of relationships at the same time. Think of it like this. If you're analyzing a complex legal document, one attention head might focus solely on the grammatical structure, the syntax.
Okay, subject-verb agreement and things like that.
A second head simultaneously focuses on the meaning, the semantics, tracking which entities are responsible for which actions. A third head might focus on the temporal aspects, tracking dates and sequences.
So you have multiple specialized lenses focusing on the same data, capturing a much richer, more complex image of the text than a single calculation ever could.
It allows the model to capture complex patterns from different abstract perspectives, which significantly enhances the depth of its contextual understanding.
But wait, if the transformer processes everything in parallel, and attention is just measuring relationships between words regardless of their position, it loses the sequential order of the original text. It wouldn't know if the input was king the or the king. That sounds like a disaster for grammar.
That's the critical piece of the puzzle we have to solve, and it's addressed by positional encodings. These are little snippets of information often generated using complex sinusoidal mathematical functions or sometimes learned vectors that are mathematically added to the input embeddings before the attention mechanisms process them.
They act like sequence markers, preserving the order.
Exactly. They ensure that tokens are interpreted correctly based on their position in the sequence, which is absolutely critical for tasks like machine translation or logical inference, where sentence structure and word order are paramount.
We've established the transformer generally, but the architecture is typically split into two primary components, encoders and decoders. How do these functional units work together?
They enable what we call sequence-to-sequence tasks. The encoder is the comprehension unit.
The reader.
The reader, yes. It processes the input sequence entirely, using self-attention to build a rich, abstract representation of the context. Think of it as a highly specialized translator reading and fully understanding the source language text. It captures the intent.
And the decoder is the writer.
The decoder is the generation unit. It generates the output sequence one token at a time autoregressively. Critically, it uses attention mechanisms that look at both the abstract context from the encoder and the tokens it has already generated so far. This structure is applied heavily in high-stakes tasks like machine translation, where you need to input a full sentence and then output a full sentence.
That clear separation between comprehension, the encoder, and generation, the decoder, is fundamental.
Now that we understand the internal engine, let's talk about its practical capacity and how we control its creative choices. Since the LLM has to look at every token to provide context, there must be a finite limit to how much text it can handle at once. That limit is the context window.
The context window.
Right.
The LLM's working memory or short-term memory. We hear about massive context windows today, 32,000, 100,000, even millions of tokens. What's the tangible benefit of this massive increase in memory?
It matters immensely for two things: coherence and instruction following over long tasks. A larger context window allows the model to maintain thematic coherence across sprawling summaries, lengthy dialogues, or when analyzing a whole code repository.
It won't forget what I told it on page 1.
It means the model won't forget the instructions you gave it 20 pages ago.
But we established earlier that this dramatically increases computational cost because of that quadratic auric complexity.
Precisely. This is the central trade-off in deployment. You get better coherence, but the cost to process or even just retrieve information from a 100,000 token window is orders of magnitude higher than a 4,000 token window.
So balancing window size and efficiency is the defining challenge for practical LLM deployment.
It really is.
Speaking of definition, the fundamental behavior of an LLM is determined by its initial training objective. Our sources highlight two primary, functionally different approaches: masked language modeling and autoregressive models. How do these training approaches shape what the model is good at?
Masked language modeling, or MLM, is what models like BERT were built on. The training technique involves deliberately hiding or masking random tokens in a sequence and training the model to predict them based on the context before and after the missing word.
So it gets a complete bidirectional view of the sequence. It can look both ways.
Yes. This fosters incredibly deep comprehension of semantic relationships. MLM models are ideal for understanding tasks. Things like sentiment analysis, complex question answering where the answer is embedded in the text, or classification.
They know what the text means. They're for analysis.
They are inherently designed for analysis.
And the autoregressive approach, the GPT approach.
That's the classic next word prediction. Autoregressive models predict tokens sequentially, strictly based on the tokens that came before them. They are inherently unidirectional. They only look backward.
Okay.
This method excels in generative tasks: text completion, essay writing, coding assistance, storytelling. They're designed to continue a sequence naturally and fluently.
That distinction is incredibly important for listeners. MLM for analytical comprehension, autoregressive for creative, fluent creation.
Yeah.
And there's also next sentence prediction, or NSP.
NSP was used in the early stages of pre-training models like BERT to improve long document understanding. It trains the model to determine if two sentences presented together are consecutive in the original text or if they are unrelated random pairs.
So it's a coherence check.
Exactly. By testing 50% positive and 50% negative pairs, the model learns relational coherence between sentences, which is vital for maintaining flow in dialogue systems or stitching together meaningful summaries.
Once the model is trained, we need to control the generation process. When an LLM has 100,000 possible next words, how do we use decoding strategies to ensure it chooses the best one?
We start with the baseline, greedy decoding. It's simple. At each step, it just selects the single most probable word. It's fast and deterministic, but
the result is often incoherent.
it's often incoherent.
Because it's too short-sighted. It's the linguistic equivalent of always taking the nearest exit off the highway, even if that exit leads you into a swamp and you miss your destination entirely.
That's exactly right. It gets trapped in locally optimal choices that lead to globally suboptimal, repetitive, or nonsensical text. So to fix that, we use beam search.
Yeah.
Instead of picking just one word, beam search keeps the top caller candidates, the beams, at each step.
So if KK $5, it tracks the 5 most likely sentence sequences at the same time. It explores multiple paths before committing to the one with the highest overall probability at the end.
That's the power of beam search. It improves coherence immensely because it balances the local probability of the next word against the global probability of the overall sequence.
So it's great for tasks like machine translation or formal summarization where you need high fidelity.
Exactly.
Beyond choosing the path, we can also control the model's creative personality using a very interesting hyperparameter called temperature.
Temperature is often called the creativity knob. It controls the randomness of token selection by mathematically smoothing or sharpening the probability distribution before sampling.
So if I turn the temperature way down, say at 0.1, what happens?
A low temperature makes the model extremely conservative and deterministic. It favors only the highest probability tokens, producing predictable, highly repeatable outputs.
Good for facts, maybe.
Ideal for tasks where accuracy is paramount, like extracting data or running unit tests.
And if I crank it up to 1.5?
A high temperature flattens that probability distribution, giving even low probability words a chance to be selected. This dramatically increases diversity and randomness. That's where you get either gibberish or truly innovative poetry.
So there's a sweet spot.
Most users find that setting the temperature around 0.7 or 0.8 balances creativity and coherence. It's ideal for storytelling or general content generation.
And finally, we have 2 variations on how to pick those tokens: top cake versus top sampling.
Top is straightforward. You define a number killer, and the model only considers the top most probable tokens, say the top 20, and samples randomly from just those.
Controlled fixed diversity.
Right. And top-egg or nucleus sampling is the smarter, more flexible option.
How so?
Top-egg dynamically adjusts the selection pool based on context. It chooses tokens whose cumulative probability exceeds a specific threshold $2. For example, let's set $P$9555. If the model is predicting the word after a highly constrained phrase like the sun rises in the law, the distribution is highly peaked around east. East might have a 98% probability.
So it's basically the only option.
Right. In this case, top will only include east because its probability already exceeds 95%. The selection pool is tight.
But if the prompt is open-ended, like she felt a sense of, where the next word could be joy, dread, curiosity, the distribution is flatter.
Precisely. In that case, top will select a much larger set of candidates, maybe 50 or 100 words, until their combined probability hits 95%. This offers flexible diversity for creative writing while ensuring the choices remain highly coherent. It adapts its creativity dynamically, which is a massive advantage.
We've built the model, and we know how to control its output. But the sheer astronomical size of these models means that training and, crucially, adapting them is incredibly resource-intensive. Let's talk about the challenges of fine-tuning, starting with the existential threat of catastrophic forgetting.
Catastrophic forgetting is the developer's nightmare. It's what happens when you try to fine-tune a massive generalized LLM, say, one that knows everything about the world on a very specific new task, like summarizing niche legal documents. The focused, intense learning on the new task can cause the model to literally erase or overwrite its prior general knowledge. It becomes brilliant at law, but forgets how to speak basic English or count to 10.
That's a massive waste of the original multi-million-dollar training investment. So how are researchers mitigating this?
There are three main strategies. First, the most straightforward is rehearsal. During fine-tuning, you just mix a small percentage of the old general data with the new specific data. This forces the model to constantly rehearse its core skills.
That seems necessary, but kind of inefficient.
It is. So the second, more sophisticated method is elastic weight consolidation, or EWC. This technique identifies the model's weights, the parameters that are critical for its core knowledge. EWC then penalizes any attempt to change those critical weights too much during fine-tuning.
So you're telling the model it's okay to adjust these 100,000 weights for the new legal task, but these core 10,000 weights that define your understanding of language, don't touch them.
Precisely. You prioritize and protect the knowledge. And the third strategy leads us directly into efficiency breakthroughs, modular architectures.
How does that work?
Instead of overwriting the core model, you freeze the base model entirely and just add small, task-specific modules on top. You avoid the overwrite problem altogether.
And that last point leads us directly to the star of modern efficiency, parameter-efficient fine-tuning, or PEFT. Why is PEFT so critical for the democratization of AI?
PEFT is the key to scalability for everyone outside of a handful of tech giants. Traditional fine-tuning means updating all billions of parameters, which takes massive computational resources and time.
Right.
PEFT methods, most famously LoRA, low-rank adaptation, update only a tiny, specialized subset of parameters, often less than 1% of the total, while freezing the massive base model.
So we keep the enormous core brain intact, and we only attach a small, specialized, and highly efficient peripheral module for the new skill.
Exactly. It saves incredible time, power, and storage. And the evolution of LoRA to QLoRA is the actual breakthrough that democratized state-of-the-art LLMs. QLoRA extends LoRA by applying quantization, specifically 4-bit precision, to the base model's weights.
Wait, let me make sure I capture the scale of this. Quantization means compressing the model's weights into fewer bits. What does that 4-bit precision mean for the listener in terms of real-world constraints?
It means enormous memory savings. Quantization dramatically shrinks the model's footprint. The combination of LoRa's efficiency plus QLoRa's compression allows practitioners to fine-tune a massive 70 billion parameter model on equipment previously considered utterly insufficient.
So instead of needing a massive cluster of high-end 80 gig upperized GPUs, QLoRA enables fine-tuning on a single standard consumer-grade GPU with maybe 24 GB of memory.
That is the key insight. QLoRA turns an inaccessible multi-million-dollar process into something achievable for small research labs or even individual developers. It is the core technology driving the explosion of specialized, smaller LLMs right now.
That is truly revolutionary. It moves LLM development out of the domain of only a few multi-billion-dollar companies and into the hands of many. Now, let's talk about building LLMs that are truly gargantuan but still manageable. The mixture of experts, or MoE architecture.
MoE is a conceptual game changer in scaling. It's a novel way to achieve massive size, trillions of parameters, without suffering the crippling proportional increase in cost per query.
How does it do that?
It works by using a gating function to activate only specific expert subnetworks, or experts, per input.
So if I submit a prompt to a MoE model about complex particle physics, only the handful of subnetworks specialized in science wakes up, and the rest, the medieval history expert or the creative writing expert, stay asleep.
That's the high-level view. The gating mechanism dynamically routes the input tokens to the 2 or 3 most relevant experts in the network. The result is that per query, only a small fraction of the total parameters, often less than 10%, are actually used.
Wait, so the model has 1 trillion parameters, but I'm only paying the computational cost for 100 billion of them when I submit a question.
Precisely. This allows for the creation of extremely large, knowledge-rich models that are still incredibly performant and efficient during inference. MoE fundamentally changes the trajectory of model size. It's about specialized, intelligent pathways now, not just one giant, slow brain.
That's an amazing optimization. Another fascinating one, related to vocabulary size, is adaptive softmax.
Adaptive softmax focuses on optimizing the output layer, especially for models with vast vocabularies. It recognizes that in any language, a small number of words like the and a are predicted constantly, and a massive number of words are predicted infrequently.
And the solution?
Adaptive softmax groups these words by frequency. It handles the common words in one computationally efficient head and the rarer words in separate, less frequently calculated clusters. This drastically reduces the computation cost for those rare words, speeding up the entire output process.
Okay, the models are now efficient, massive, and modular, but we need to address their biggest ongoing failure: factual accuracy or the dreaded hallucinations. How are we integrating tools to make LLMs smarter and more truthful?
We're using several primary techniques that rely on connecting the LLM to the external world. The first is retrieval augmented generation, or RA.
The fact checker.
This is the leading strategy to turn the LLM from a closed-book test taker into an open-book fact checker.
Walk us through the RA process, because this seems like a fundamental architectural shift.
It happens in 3 distinct steps. First, retrieval. Using the query's embedding to search an external trusted database of verified documents.
Right.
Second, ranking. Those retrieved documents are sorted by relevance. And third, generation. The LLM doesn't answer based on its internal memory alone. It uses the retrieved verified text, which is fed into its context window, to generate the final accurate response.
So RA is crucial because it gives the LLM external, up-to-date, and verifiable context.
Yeah.
It dramatically reduces factual errors because the LLM is fact-checking itself in real time.
Absolutely. It mitigates the hallucination problem and provides verifiable citations, which is critical for enterprise and research applications.
The second strategy involves integrating structure using knowledge graph integration.
Knowledge graphs provide structured, factual data. Think of them as high-fidelity semantic networks of entities and their explicitly defined relationships, like Paris is the capital of France.
Map of facts.
Integrating these graphs enhances the LLM by validating facts against this structured map of reality. It reduces hallucinations and improves complex logical reasoning.
And the third strategy is about guiding the model's internal processing itself. Chain of thought, or COTNI prompting.
COTNI prompting is a psychological breakthrough in reasoning. It guides the LLM to solve problems step by step, mimicking human logic. If you give it a complex math problem, you don't just ask for the answer, you prompt it to think out loud and break down the calculation.
And the result isn't just a better answer.
It's a higher probability of getting the correct answer because the model forces itself to follow a logical path. This drastically improves accuracy in complex reasoning tasks and also improves interpretability. You can see where it went wrong.
Speaking of advanced models, we have to touch on the evolution towards multimodal AI. What defined the shift from a text-only world to including images, video, and audio?
GPT-4 was the major inflection point. It added true multimodal input. It could process text and images simultaneously and understand the relationship between them. It also significantly scaled the context window, going from GPT-3's 4,000-ish tokens up to 25,000.
A huge jump in memory.
And the next step we're seeing, covered in our sources by models like Gemini, focuses heavily on optimization in multimodal training.
How do they achieve stability and efficiency when combining such different data types?
Gemini focused heavily on a unified architecture, combining text and image processing seamlessly within the same network weights. This improves parameter efficiency dramatically.
I see.
Furthermore, it uses advanced attention mechanisms tailored for cross-modal learning stability and prioritizes data efficiency by utilizing self-supervised techniques, which reduces the reliance on expensive human-labeled datasets.
We've covered the amazing technical innovations, but we need to pivot to the reality of deploying these behemoths in the real world. Despite LoRA and QLoRA, the challenges remain sobering.
They really do.
Our sources list the core deployment headaches. First, resource intensity remains a massive hurdle. Even if QLoRA helps one person fine-tune, running a trillion-parameter MoE model at scale for billions of users still costs a fortune.
Absolutely. And then we move to the non-technical but critical issues. Bias is a huge risk. These models are essentially highly effective mirrors of the data they consume, meaning they inevitably perpetuate biases, racial, gender, cultural present in their training data.
And the black box problem.
Interpretability. It's still a defining weakness. It is incredibly difficult to explain why the model made a specific, critical decision. This lack of transparency undermines trust, especially in high-stakes fields like medicine or finance. And finally, privacy remains a concern.
So if you, the listener, are responsible for deploying an LLM and you see it generating biased or incorrect outputs, how do you practically address that?
You need a structured, multi-pronged approach. First, analyze patterns. You must identify where the bias is coming from. Is it the data or is it the prompts?
Okay.
Second, enhance data. You must use balanced data sets, apply specialized debiasing filters. And third, fine-tune strategically. Retrain the model using small, carefully curated data sets designed specifically to expose and correct those deep-seated biases. It's an ongoing process.
Let's clarify a fundamental conceptual distinction that helps understand the broader AI application space.
Yeah.
The difference between discriminative and generative AI.
Discriminative models, like specific applications of BERT, focus on predicting labels or categories. They model conditional probabilities. They answer the question, what is the probability of outcome Y happening given input X?
So accurate classification.
Right, predicting sentiment, identifying objects, that kind of thing.
And generative AI, like GPT or DALL-E, is fundamentally different.
Yes. Generative AI creates new data entirely. It models joint probabilities. It answers the question, what is the probability of X and Y existing together? They're suitable for creation and content generation fluent, novel text, or entirely new images.
This entire ecosystem, built on transformers, is now broadly categorized under the term foundation models. Just to recap the sheer scope we've covered, what are the primary domains that rely on these core concepts?
They span the critical areas of AI development. Language models like GPT-4, vision models like ResNet, generative models like DALL-E, and the increasingly dominant multimodal models like Gemini and CLIP, which bridge text and images. All of them rely at their core on attention and scale.
We've spent this entire deep dive discussing the LLM's vast internal mechanics, but let's bring it full circle back to the listener. The main lever you have to control this massive complexity is prompt engineering.
Prompt engineering is the critical interface. It is the specialized art and science of designing your inputs, your prompts, to reliably elicit the specific desired LLM response. You are translating your intent into a format the model can efficiently process.
And prompt engineering is vital because it enables the model to perform tasks it wasn't explicitly trained for, through concepts like zero-shot and few-shot learning.
Zero-shot learning allows the LLM to perform completely untrained tasks using only its general knowledge. For example, asking it to translate this Hungarian phrase into English and categorize the tone as formal or informal, even if you never explicitly trained it on Hungarian translation or tone classification.
It's extrapolating from its vast general knowledge, and few-shot learning takes that one step further.
Exactly. Few-shot learning is when you provide minimal targeted examples, just one or two specific input-output pairs directly within the prompt itself. This allows the LLM to adapt instantly to highly niche or specific stylistic requirements.
The benefits are massive.
Reduced data needs, faster adaptation, and cost efficiency for specialized niche applications. Prompt engineering, paired with these learning techniques, is the mastery layer that unlocks the LLM's immense capability for individual users.
Okay, let's unpack this and bring it full circle for you. We started with tokens and built our way up through the revolutionary attention mechanism, that core idea that allows a machine to focus and process long-range dependencies in parallel.
Mm-hmm.
We established that the resulting quadratic computational cost is the biggest hurdle to scale, which led us directly to the critical efficiency hacks.
What's fascinating here is the evolution. The narrative is shifting away from pure brute force scale. We covered QLoRA, which democratizes advanced AI by putting 70 billion parameter fine-tuning on a single GPU. We discussed MoE, which makes trillion parameter models efficient to run. You are not just talking to a static, monolithic model anymore. You are interacting with a highly optimized, context-aware engine that uses RAG for external fact-checking and CUDI for complex, traceable reasoning. These clever modular add-ons are defining the quality and sustainability of the modern LLM experience.
The source material highlights that the biggest challenges are now resource intensity, bias, and privacy. But looking at the trajectory of the solutions, the rise of modular MoE architectures and the reliance on RAG, we are clearly moving away from seeking only the largest possible number of parameters and towards smarter, more specialized components.
That's the key shift that we should all be watching. The future of LLMs isn't about the biggest number, it's about the model that is the most modular and efficient for real-world application. The integration of external tools and specialized internal experts signals a major change. LLMs are becoming platforms, not just models.
So what does this mean for the next generation?
Focus less on how big the model is, and more on how intelligently it uses its parts, and how effectively it connects to external, verifiable sources. The modular approach is the future of sustainable AI development and the key to solving the practical limitations of today.